All right, this video note is going to be how to work through gas problems, and we're going to be using the combined gas law. And remember, with the combined gas law, we can use it for any gas problem when we've got the same number of moles or molecules. That's always going to be a constant. If we're doing one of these problems and you'll see that we're missing some factors, like if volume isn't mentioned in a problem, then we can actually cross that out. Let me show you how that works. So the first thing I'm going to do is read my problem, and I'm actually going to underline the factors in the problem. So an aerosol can carries warnings on their labels and says not to incinerate or burn them and to store the cans above a certain temperature. The gases used in the aerosol can is at a pressure of 103 kPa at 25 degrees Celsius. If a can is thrown into a fire, what will the pressure be when the temperature reaches 928 degrees Celsius? So the next thing I'm going to do is write my combined gas law. P1 V1 over T1. So my pressure, volume, and temperature at the start will equal my pressure, volume, and temperature at the end. So I'm reading my question. You'll notice that I only have 4 things underlined. I've got pressure underlined, temperature underlined. Volume is not mentioned or is not changing in my problem. So I can actually cross out this value in my equation, which means that my relationship I'm going to be looking at is pressure over temperature. So let's go ahead and figure out what values I'm going to be using for my problem. P1 is going to equal 103 kilopascals, and the temperature one is going to equal 25 degrees Celsius. But I can't just leave it at 25 degrees Celsius. Remember, all gas problems have to be completed in degrees Kelvin. So I need to add 273 degrees to that, which equals 298 degrees Kelvin. My pressure 2, my ending pressure, is what I'm going to need to find out. Temperature 2, I'm given, again, it's 928 degrees Celsius. I need to convert that to Kelvin, and that's 12,001 K. Now all I have to do is I have to just plug this into my formula. So 103 kilopascal over 298 degrees Kelvin is equal to, I'm solving for that, so I can just substitute that in my P2 over my temperature, 1,201 degrees Kelvin. Now the next thing I like to do is I like to try to get rid of as many of these units as possible. So I'm going to look at my formula, and if I see that I've got the same unit on one side of the equal sign as I do on the other one, I can actually kind of get rid of it and not keep that with my number. This way I know the only unit I've got left is kPa, so that's going to be the unit that I'm going to need with my answer. So let's go ahead and solve this problem. Remember when you were in algebra, in order to solve a problem with an unknown, with 2 fractions, you're going to cross multiply to get your answer. Which means when I do this problem, it's going to be 103 times 1,201 equals 298 times my unknown. In order to solve this, in order to solve this, I'm going to go ahead and I'm going to multiply 103 times 1,201, and the number I get is 123,703. Now, in order to get rid of, because remember I want to isolate my unknown, in order to do that, I'm going to need to divide this side by 298 so that that'll cross off. If I divide that side by 298, I need to divide this number by 298. And when I do that, I'm going to get my answer, which is my unknown is going to be 415. Now I also have to look at my significant figures. I have two significant figures, so I'm going to need to round this, which means my final answer is going to be 420 kPa. Let me put a box around that. Let's go ahead and try number 2. Right there. Again, I'm going to annotate my question. The pressure in a car tire is 198 kPa at 27 degrees Celsius. After a drive, the pressure is 225 kPa. What is the temperature? And again, it tells me that I'm going to assume that the volume is constant. So when I'm doing my formula here, in this particular question, volume is constant, so again, I'm going to not need to use volume in this formula. So let's go ahead and just plug these numbers in. So P1 is 198 kilopascals. Temperature 1 is 27 degrees Celsius plus 273. So 300 Kelvin. Pressure 2 is 225 kilopascals. And I'm going to solve for temperature 2. I substitute these numbers in. Now I'm going to look at this and I'm going to try to get rid of any units so I'm left with the unit that I want. I've got kPa on both sides, so I'm going to cross off that unit. So I'm left with degrees Kelvin, and that'll be the unit for my final answer. I'm going to go ahead and cross multiply. And now, in order to get rid of the 198, I'm going to need to divide that by 198 so I can get rid of it. And then I'm going to need to divide that by 198. And that'll isolate my second temperature so I can get my answer. Now I can put that in my calculator, and 300 times 225 equals divided by 198. So my answer is going to be 340. And I'm going to look for my significant figures. I need two significant figures. That answer has two significant figures. So my final answer is going to be 340 K degrees Kelvin. I'm going to skip over number 3 and I'm going to go ahead and do number 4. And leave the rest of the problems for you. Again, on this sheet, you're going to do all the problems. So this is the last one I'll demonstrate. This one's a little trickier because when we first annotate this problem, find the volume of gas at STP. If its volume is 80 milliliters, 109 kilopascals, and negative 12.5 degrees Celsius. Well, when I'm underlining my variables, 1, 2, 3, and I need to find the volume, there's my unknown, it looks like I don't have quite enough information because I've got 3 things here and I seem to be missing some factors. Well, the factors are hidden in this STP. Remember, that stands for standard temperature and pressure. So standard temperature, if you look at your notes, is 0 degrees Celsius or 273 degrees Kelvin. So I know this is a gas law problem, so I might as well use the 273 degrees Kelvin. The other one is standard pressure. And again, if you're looking at your notes, standard pressure is 1 atmosphere, 760 millimeters of mercury, or 101.3 kilopascals. Well, the other pressure that I've got here is kilopascals, so I might as well use that so I don't have to convert anything. So 101.3 kilopascals. So these values are hidden in that STP. I just have to know what standard temperature and pressure is. So let's go ahead and fill in our values. Our formula is going to be P1 V1 over T1 is equal to P2 V2 over T2. So these are the pressure, volume, and temperature at the start, and pressure, volume, and temperature at the end of it. Now let's see what values I need to substitute in. P1 is equal to, so pressure 1 is equal to, I'm going to put these three factors together. So that's going to be 101.3 kilopascals. My temperature 1 is going to be 273 degrees Kelvin. My volume that's going with these is going to be my unknown. Pressure 2 is going to be the 109 kilopascals. Volume 2 is going to be 80.0 milliliter. And temperature 2 is negative 12.5 degrees Celsius. Of course, that one I have to change into Kelvin. So I need to add the 273. So negative 12.5 plus 273 is 260.5 Kelvin. So now I'm ready to substitute in my values and just solve the equation. So P1 times V, well, that's our unknown, over my T1 temperature, 273 Kelvin, is equal to 109 kilopascal times my volume, which is 80.0 milliliters, over my temperature, which was 260.5 Kelvin. So again, I'm going to go ahead and solve this. But before I do that, I want to get rid of as many of these units as possible. So I've got kilopascal over here and kilopascal over there. We can get rid of those. I can also cross off my units Kelvin. So I'm going to be left with milliliters as the only unit that I've got. So milliliters is going to be the unit I'll need with my answer. So the next thing to solve this problem, I'm going to cross multiply. And it doesn't matter which direction you go in for this, but I'm going to go 101.3 times my volume times 260.5 equals, I'm going to cross multiply these now. Some people in class were calling it butterfly. If that's the way you remember how to do this, then that's great. Whoops, let's switch to black. So 273 times 109 times 80.0 in milliliters. So we can go ahead and just solve this. In order to get the 101.3 to cancel out, I'm going to need to divide this side by 101.3, which means I'm going to need to divide this side by 101.3. In order to get this to go away, So I've taken care of that one. Now I need to divide this by 260.5. Now this one will cancel out. And now I'm going to need to do the same thing to this side. So I'm going to need to divide this answer by 260.5. And what that'll do is it'll isolate my variable. So my V1 is going to equal So when you put this in the calculator, you're going to get an answer of 90.2 milliliters. So you're going to go ahead and you're going to do the back side of the sheet. I'm going to go ahead and I guess we'll just do that and bring this in and we'll take a look at what you did. None of the problems should be any more difficult than the ones that we've demonstrated here.